अब वो सर ज्वाइन हो गए।
हाँ कितने पार्टिसिपेंट कितने ज्वाइन हुए?
पार्टिसिपेंट तो अभी 13 ही लोग हुए।
उसमें डालना ऑल प्लीज ज्वाइन इमीडिएटली।
डाल
स्पीकर
दी।
स्पीकर के बारे में और स्पीकर ऑलरेडी ज्वाइन द सेशन। 17 स्टार्ट कर दें क्या?
कर दो वो कर होते रहेंगे तो।
17 ही है ना?
कर दो, हो जाएंगे ज्वाइन। फिर टाइम पे स्टार्ट होना जरूरी है।
एक्चुअली जो लोग छोड़ के चले गए थे ना, उनको लग रहा होगा कि Good afternoon, sir.
Hi, good afternoon. Can you hear me?
Yeah, yes, sir, yes, sir. Uh,
Okay. So I'll be just
okay,
sharing a slide just once that I want to see,
okay,
are you able to see or not? Okay.
okay.
Are you able to see the slide?
Yes, sir.
Okay,
Uh,
I'll just change the slide, just you let me know it is moving or not. Okay. It is moving.
uh,
I'm changing the slide.
uh, uh, Actually, it's just blank. It is totally black color.
Okay, I think
We are
just
not
I will
able to
check
see.
it. 1 minute. Because some animations are there, I was looking how I'm going to play. What about now?
Yeah, yeah, yes, sir. Now it's okay.
Okay, I'll just check
Okay,
it because some animation, how it is going to work, I need to check it. Okay. In a Google Meet, sometime I have struggled that this animation don't work. So, yeah. Okay. Okay.
okay. Uh, Dear participants, Department of Information Technology, SSTC Bhilai, welcomes you all on the second session of this 1 week online faculty development program on technological innovations of artificial intelligence in medical diagnostics under AICT Atal Academy program. And in this session, we have our esteemed professor, that is Professor Dr. Anil Kumar Saw sir. He is associate professor in IIT Mumbai. Dr. Anil Kumar Saw is presently working as an associate professor in the Department of Electrical Engineering and Computer Science, IIT Bhilai. He received the bachelor's degree in electronics engineering from GEC Raipur, Chhattisgarh in 1999 and the master's and PhD degree from the Department of Computer Science and Engineering, IIT Madras, Chennai in 2004 and 2010 respectively. Prior to the joining IIT Bhilai, was in School of Computing and Electrical Engineering, Indian Institute of Technology, Mandi. He had served as chairperson of the school during 2013 to 17 and associate dean during 2018 to 2020. The research works of Dr. Saw are in the broad field of sparse representation, image super resolution, magnetic resource imaging, functional MRI, and pattern recognition. The funding of his recent research has come from various sources, including Defense Research and Development Organization, Department of Electronics and Information Technology, AIN DRA Private Limited, and he has more than 70 research publications in various reputed journals and conferences. He has supervised 5 PhD scholars and 4 MS students, and who are further working in the reputed research organizations. So, we welcome you, sir. We welcome you in this session, sir. And The topic of the session will be various techniques in the diagnostic prognosis of disease. Over to you, sir.
Thank you. Thank you very much. Am I audible?
Yes, sir.
Okay. So, mm, uh, should I switch on my camera? How to optimize in order to optimize the bandwidth? How do you want me to do?
Sir,
Uh, I mean, like, as you feel, I hope because due to video, the bandwidth is not well optimized. So you tell me, should I switch on or I can switch off, whichever way?
sir, as you want. Um, if the camera will be on, then it will be
Good.
good.
Okay, that's great.
Okay.
Well, that is fine. So, okay. So, thank you very much for the kind introduction. And it's my great pleasure that I am with all of you. Thank you very much for inviting me on this 1 week activity development program. Okay, and like I remember almost 6 months back, I got an email, and I was asked to give presentation. So this is my hometown, so I agreed immediately. I thought I'll be definitely able to come here. Then situation happened in such a way that I joined IIT Bhilai. So just a small correction when I was introduced. So I have joined IIT Bhilai. Okay. So I'm there, and with this background, I would like to begin. So the title which I have chosen is Challenges to restore the high field MR images from the given low field MRI images. है ना? So basically, I'll be dividing the entire talk in a two part. One is MRI, structural MRI. I will give some deep background. And one more thing I want to say, I'm not from the medical background, so my knowledge is limited on the medical side. However, I'll be taking on the machine learning and pattern recognition, signal processing aspect of when we process these MRI images. Then I will also talking about it something on a functional fMRI. Okay, functional fMRI and what challenges. Well, there's some work which has been being carried out by with some of my students that also I'll present. Okay, I hope. Okay, so here I think we can like how the question will be taken care. I just am curious to know. And
So, if uh, if there's any question or any query, then you can put in the chat box or
great.
through the speaker. Also
Sure,
ask for
sure.
the speaker.
Okay, great. है ना? So that is what all the participants, please do type your question, and if at all you have something, you can raise the hand and I can address your query. Okay. And one more thing is like this. I'm going to give like in a bigger picture. uh, because going too much micro level may not help it. But as the situation, as the presentation will go, um, I'll be glad if you can make it interactive, and if you have any questions, we'll be happy to answer on that. Okay, so that's right. So, looking at this talk, I look at it. So, I want to say that this particular work, which I am going to share, uh, it is basically. Are you able to see my mouse? I'm just trying to look at it. Are you
Yes.
able to see mouse
Yeah. Yeah.
when I'm moving? No, you are not able to see when I move the mouse.
Yeah. No, it's visible. We can see that.
Okay, great, great. Thank you, thank you. So here, probably we'll spend an hour and then we'll take a break and then we'll continue further. Hmm. So this talk, basically, I want to say that the work has been carried out. So they are my collaborator, especially one Dr. Chirag Kamal Ahuja. He is a doctor in PGMIR Chandigarh because when I was in IIT Mandi, I used to interact with him. So he has collaborated and he has really helped me to improve my understanding of this problem. Then I have another colleague named Dr. Atul Singh Minhas. He is a faculty in Macquarie University, Australia. Basically, he was a person who had worked in Siemens, where he was playing a active role in designing the MR scanner. And MR means when I say medical resonance image scanner. So he has really helped to uh, formulate this problem and how what other things are going. So both of us have some publication on this. And majorly the work which has been carried out by Prabjot Kaur, PhD student. She submitted thesis and now her review also has come, so she is going to graduate. So my number is going to be from 5 to 6 very soon on that. Okay, and they are from IIT Mandi. Okay, fine. Are you able to see this change in slide just for when I want to check it from the first? Okay, great. Are you able to see? Yes. Okay. So in this slide, how many of you have heard about MR scanner? Anytime you have used it in your life? I know it is a bad question to ask that to go to the clinic and get done some testing. And I wish that none of you should go. But it's my question that have you anyone gone through the scanner, MRI scan, maybe your parents or elder one? Any question? Anyone? Or you can write it if you feel like. Oh, none of you have gone through the MR scanner? Great, I'm happy. All of you are very healthy and that good and should be. Yeah. Okay. So my next question will be, you might have also heard about it. This whenever people, I mean, like now there are so many clinics are there and so many hospitals are there. So they write whenever they mention MRI scanner, they mean something like a zero point 0.2 Tesla, 1.5 Tesla, 3 Tesla, 7 Tesla. This I'm sure all of you might have heard about it. Am I right? Okay. Yes. Huh? So basically, this Tesla is a unit of magnetic field, and definitely all of us knows that it is in the name of our great scientist. है So here in this particular slide, I am showing it MR image that has been captured by three different magnetic field strength. Okay, the magnetic field strength, you can, this one is a zero point 0.2 Tesla image, this is 1.5 Tesla scanner, and this is 3 Tesla. Okay, and now which image you, and it is same person has been gone through the scanner, and which image has a quality is better? Can you guess someone? Yeah, please make it interactive and interesting. We'll be happy to.
3D image.
Great, nice, thank you, Lakshmi Devasana. Thank you very much. I'm happy for the question. Okay, so this, as you mentioned very well, that the quality of this 3D Tesla image is better. And why you are saying it? Can you little bit tell something? Why do you think? I mean, what thought has come to you to say that the quality of this 3 Tesla image is better than this two? Yeah. More visible than in clarity wise. Yes. So let me put it, because as you mentioned that we are not so used to looking at the MR images, and especially it has been done by the doctors. So, but you have a very much great feeling for the natural images. The moment I say natural images, I mean the images which has been taken from your normal camera, correct? And this, if you look at it, this MR images which I am showing it, so I'm just highlighting the particular box section of this region and I highlighted here. And you can see these details is almost mirrored. Okay, so this we said tissue boundaries. So basically this white region is called white matter and the other one is called gray matter. And if you read about this, the basically MR images taken from the brain, okay, and whatever the brain which is there, and in that there are different tissues are there. So we are focusing this we call as a gray matter and white matter, and you can see the tissue boundaries is much better discriminative in this is compared to this. Okay, so as I mentioned that I'm not a like a medical practitioner, but people who are in the medical domain, they'll be able to tell much better about this what it says and what it is saying. But from the engineering perspective, the point I want to emphasize, we do say that the quality of image in this 3D scanner captured by is much better than this too. Okay, so now everybody will say, okay, then go ahead. Why do you need to have a 0.2 Tesla MR scanner? let us have all the scanner in the India with a 3T SLI scanner. So in order to convey that, I'm showing this cost. Okay, so this is the cost of a 0.22 Tesla scanner, $146,000. This is 1.5 Tesla, $900,000, and then 3 Tesla, it is, you can see, $250,000, and 7 Tesla. So you can see the cost of the scanner is really going very exponential high the moment you are increasing the magnetic field strength. Okay, so definitely you want that you should get a good quality, and it has a directly implication on the diagnosis of some tumor or any other abnormality in the human brain or any part of the scanning when you do via MR. So you wish that you should get a scanner of this cost of this quality. Am I right? This makes sense. High resolution. Absolutely right. Some of you did mention. So you are looking for something to get an image which of this quality, but in the less cost. Okay. So when I'm doing this, um, as I mentioned, the cost is going very, very high. So one of the research problem which has been posed, can we reconstruct 3D like MR images from 1.5 or 2.2 test images? So basically like this, you have a MR images which has been captured uh, via this, okay, and this if you capture, can you do some kind of image processing or some kind of machine learning, what you call artificial intelligence? I would say this area, this term is very, very big meaning. And just a minute. Okay, so the point is that if I have some mechanism to generate an image like this from this image or image like this from this, okay, so what will happen, you don't have to buy the Tesla scanner. You can develop some algorithm based on the artificial intelligence and machine learning algorithm to translate this image to this image. Please note that here one fundamental thing is in MR image scanner, we have a hardware and software. Okay, so hardware is typically is very, very expensive. Why this 3TS 7TS scanner is very, very expensive? The reason being is the kind of permanent magnet or the kind of instrument with the precision which is required, that is very, very expensive. On the other hand, the scanner which you have a point to Tesla, the kind of resolution, the kind of precision you need it, you don't need that sophisticated hardware. So that's why the cost goes up. So in order to solve this problem, we are saying that okay, let's have a only point to Tesla scanner and do a machine learning algorithm because and then do transcript like this. Since machine learning algorithm or software doesn't have much cost, but it doesn't have much cost. Okay, so definitely it is going to be very, very useful. So this is what I want to say. It will be really useful for medical diagnosis with less cost. And as we know that we are processing an MR images, so in when MR images, whenever we want to process, for example, if you take a statistic of this Bhilai region, um, how many like in healthcare is there, and whenever there is some need comes for the MR scanning, not everybody has to go through the like in a highest field MR scanner like 3 Tesla, 1 Tesla. They have to like basically like there's some only need is going to be there which has to go through it, because definitely in some of the decision can be made via point-to-point Tesla. Okay, and some of the things you need to go. So basically there should be a like a little scheduling, have few high field MR scanner and lot of low field MR scanner. And then what happened, you can really trick it, and if you look at it, this quality of images, obviously you can't replace it, the image which is coming via directly hardware. You can say, okay, you can rely on. So that is the goal I want to say. Okay, and this has a benefit because you can provide a diagnosis with a low cost. I hope this part is clear with everyone. If you have any questions, okay, because this problem understanding is very, very important in my perspective. Yes. Okay. Okay. Am I audible on this? Please. Okay.
Sir, yes, sir. Okay.
Great. So when we do this, and that's what we are looking for. Okay. So I have just given a very, very broad way. Can I reconstruct a 1.5T like image from this, which will look like this? Okay. So definitely you can realize it, the amount of cushion it will give. It will reduce the load on the high field MR scanner, and your diagnosis and everything will be very, very less. So to explain it further, as I one of the parameters I use it, one of the thing I was talking about is magnetic field strength. Okay, so again this part, as I mentioned, that people they use a MR scanner and they can talk hours about this how this scanner works, and my job is to just tell you in a few minutes what does it mean from this perspective. So this MR scanner basically depends on this, that all the molecules which you have, because in brain when we take it, we have different atoms, okay, that ultimately is a smallest unit, and there is a proton. So this proton basically when it is put it under the external magnetic field, then it absorbs energy, and then what happened? They relax it, this energy get dissipated. So basically, we capture the energy dissipated from this, and there are some sensors up there. So different matters, basically they decay differently, and that is what the relaxation time or something, where different words are there. And if you go through the some of the MR image journal, this or T1 image, T2 images. So basically it says that different relaxation time. So that you can take it from this where that whenever do an MR scanning, we tune it our hardware to measure the amount of energy dissipated from that particular proton or that particular atom. Okay, so that is where there is a term called relaxation time. Now, definitely there are two magnetic field. One is called main magnetic field strength, and that's called gradient field magnetic strength. This the term which I was using it 0.5 Tesla, 1.5 Tesla, 3 Tesla. This is basically the main magnetic field strength. Okay, and there is also called pulse sequence parameter, which is going to be there. So all these parameters, they try to use in a very, very, what do you say, on a manner to optimize the quality of image. Okay. So for example, when we want to say the quality of images, there are three parameters that typically, like I want to quote it here. One is called spatial resolution. Second is called signal to noise ratio. Third is image contrast. So what do you mean by spatial resolution? Whenever we acquire an image, so how many pixels are going to be there in particular this one focus of attention? If your spatial resolution is very good, the quality of image is going to be good. Okay, and if you want to understand in a very normal image, all of you have a mobile camera. This mobile camera basically, if you mobile camera basically if you take it that we talk about now 3 megapixel, 7 megapixel, 10 megapixel, 12 megapixel. Basically here we talk about it, we have a camera and it has a resolution, how many pixels are there in vertical, how many pixels are horizontal, and this is going to take it the amount of like R into C into number of bits. So this is what is going to define the quality. So the spatial resolution, basically the smallest distance that between 2 points that we are going to get. And the spatial resolution problem, I am going to repeat it again at present. So basically, you can think about it in a voxel because it is, when you want to scan the human brain, you need to have this 3D model. Now you consider our brain has a 3D model, and this 3D model you are dividing in the smallest unit. Okay, so in a 2 dimension, you divide a small unit, that's rectangular box or called pixel. On the 3 dimensional case, the small unit is called voxel. Okay, so this spatial resolution, when you intended to say, we intended to say both pixel versus voxel size. The smallest is the voxel size, that is good for us. Okay, and that you will be able to discriminate, you will be able to find out any abnormalities on that way. Second is called signal to noise ratio. So whenever we observe this signal from the, well, like in this case, what is the signal? The energy dissipated from this particular photon that you are capturing here. So you want to devise the sensor in such a way that it should not be very, very noisy. So that is the signal to noise ratio. And third is the image contrast, which I need to say here. This contrast you can see when we are going it, so basically gradient. In this case, definitely you can see the contrast of this image is very good in compared to this. So this is what when we define image quality parameters in the context of MR images. So MR means magnetic resonance images. So basically, it is relying on the property of NMR, nuclear magnetic resonance. So when you put in a particle under the magnetic field, it resonates, it absorbs the energy, and dissipates it. The same concept has been used here. So now we can relate it when we observe the images. It is going to look like something. Okay, and this particular I did mention earlier is called white matter. This is called gray matter. Okay, and this different angle of your brain, I'm showing it here because most of the result which I'm going to discuss today, it is for the brain image only. Okay, so this all of you can appreciate that this is your like what do you say, the back side of this particular angle, and this is called sagittal view, and you can see, and this is like in a top view, and this is another view which you can call axial and coronal view. Okay, so this like this is a 3D and you want to analyze it. So basically you are chopping, you are taking cross section at the top, this side and this side, correct? And this all three angles are which are shown, you can visualize it. So this particular images I'm showing it, it was basically axial view. You can have a coronal view also, you can have sagittal view. Okay, and wherever you can see is a white matter, gray matter, and this gray matter basically it is all your neurons which are there in a human brain that is going to be there, and white matter is basically connecting this all neurons. So this is your structural MRI, so structural aspect of your human brain. And when you acquired image, basically you want this tissue should be well separated, the boundary should not be smeared, they should be less noisy. The other part, later part of this talk, we will see, will talk about the functional aspect. We will consider the gray matter region. Okay, I hope it's clear. So this is what your magnetic resonance images, we have talked about it, and the scanner which we use it, that has this property, magnetic field, main magnetic field, gradient field strength, relaxation time, pulse sequence parameter. And with all this thing, you optimize in such a way to get the best quality of images. And the best quality of images, you have these three parameters. Now, the point I want to emphasize is that there is a very thumb rule to take it because it's a very, very complicated relationship. It requires entire knowledge of the physics, where you need to understand that if you keep on increasing the magnetic field strength, the SNR will be improved. So, what is the idea? Signal to noise ratio. Okay, well, like this relation, how it comes and all these things, at present you ignore it, but you take it on this. You know? So here, basically, it says that if your magnetic field is very, very high, the SNR is going to be very good. But magnetic field is very, very high, then you need to have an appropriate hardware. That hardware is basically is going to be expensive. The second part is gradient field also is comes, and they are going to play the role of the resolution, high resolution. And then the T1 and T2 parameter, all these things is going to look at it here. Okay. Then when we talk about the spatial resolution, another thing comes it's called, because when we acquire an image, you acquire over temporal time also. You don't take in only one image, you take it several images. So the entire relaxation time when it goes, you need to take one more scanning of that. It's like a video. Okay, it's like a video. So as we know that whenever we are observing a video, so what happens if you are with some quantity called video in FPS, frame per second, you know? So frame per second means 30 frame per second or 50 frame per second. So the camera which you have it, you record it. If your frame per second is very high, in how many frames per second you can keep it, you will be able to capture a very minute variation If your FPS is very, very small, you cannot be able to do it. So similarly, you can see here your FPS is not determined by this hardware, but is determined by this entire inertia of your natural system. Because the moment you excite it and it decays down, so you cannot take the next sample immediately. You need to wait for this. Okay, so this is called temporal resolution. And if you want to associate with respect to your medical diagnosis, you think about that you need to be put up in the scanner for longer duration, okay, and you don't want basically. So I hope this initial background is clear
यहाँ
to
नहीं है
everyone
CSC लैब
that what is MR images and what are the different fundamental properties that has been used to acquire and what are the different parameters that comes in picture. Okay, am I making sense here? Okay. So going further, here I want to illustrate two things. That can I improve the signal to noise ratio? Can I improve the contrast? Can I improve the resolution? Three problems are going to come. Okay, and this you can see from this particular case. So the research problems in my perspective, which people have done, and I like to highlight it. One is called improving resolution. So here it is possible that for a given magnetic field strength, you can acquire image with a low resolution. So what are the immediate disadvantages going to be there? You need to ask a person to be in the scanner under long duration. In addition, there are now several guidelines that you can't put a human being under scanner for longer duration. It may have some adverse effect also. Okay, so and then also because you have so many people to get it through this MR scanning, so you don't want to ask the patient to sit for long to wait for the longer duration. So you want to quickly scan it. So that is way you can think about this a problem that you have acquired an image, low resolution images for a given magnetic field, and then you are asking that okay, can I improve the resolution of the images with this? That is one thing. Second thing is, can I improve the signal to noise ratio? Correct. So this is again what happened when we acquired this image, the MR scanner. So if your resolution, the voxel size is very, very small, so what happens, you are trying to basically measure the emitted energy with a very small location, and it can be noisy also. So that's why you don't want to acquire in a very minute location, you want to put it a little bit bigger. Okay, and when you want to take a little bit bigger, then it will average out. So you need to strike a balance that you don't want to be very, very small size of boxer as well. You don't want to go bigger because in this case it will average out. In other case you may capture a noise also. The one problem which people pose it that okay, for a given magnetic field strength, can I get a low resolution images and improve this resolution? Or given this one, can I get a like a poor SNR and then I can get it? Yeah. Anyone has a question? Someone? Yeah. I felt someone was asking a question. No? Okay. I can continue then. Okay. So that is one problem. The second problem, I am acquiring the image from the low magnetic field strength as well as high magnetic field strength. Now the goal is that can I transform on images that has been acquired with the 3 Tesla scanner and it looks like 70 Tesla scanner. So this is what the problem. So here I can talk about can I go to 3 Tesla to 7 Tesla? I can go to 1.5 Tesla to 3 Tesla. Either go to 1.2 Tesla to 1.5 Tesla. So one of my question at present is that which problem do you think is going to be most challenging and difficult? Can somebody answer on this? Yeah. If somebody can point it out, that which problem is going to be most challenging or going to be very difficult as compared to that problem. No? Yes. Can't hear. Hello.
So the artifacts.
Hmm. Yeah, so I'm just asking among this problem, which problem is going to be most challenging in your perspective? Hmm? Yeah, please do answer. Any guess also is fine. I will answer this. I don't know. Nothing. Yeah, are you able to hear me or not? Am I audible there?
Yes, sir, you're audible.
Yeah. So, Dr. Guru,
Yes, sir, you are audible.
and thank you. So I just want to know, like, anybody can guess it. That's what my question I have put up. Okay, let me move on then. So here, definitely, I would say that this problem is going to be much more challenging than this problem. Okay, and in addition also, you need much more sophisticated algorithm if you want to translate an image of a zero point 0.2 Tesla scanner to 1.5 Tesla scanner as compared to this, because the degradation which happen on the low magnetic field is going to be very, very severe, and you have to restore it back, which is going to be much more challenging as compared to this. So the difference between quality of 3 Tesla and 7 Tesla is going to be very minimal as compared to the 0.2 Tesla to 1.5 Tesla. And one more point I want to emphasize is that in India, still most of the places they use 3 Tesla, 1.5 Tesla. 7 Tesla is not much used for the human. I mean, like, so with this background, I hope I have tried to clarify. I have clarified the different research problems which are there. Yeah, which are there, which we can use to solve this problem for this improving the resolution or improving the SNR or improving the contrast. Okay, yeah. I think all of you can appreciate of the research problem till now which I have mentioned. Okay, fine. So if you look at it very fundamentally from the image processing perspective, you can think about it as the image restoration problem. Okay, image restoration problem means there is some image got degraded due to some operation, and can you do Fourier processing or can you do a processing on the degraded images which will look like to the original image? This is called image restoration. So you are trying to restore it. In another way, when I'm speaking, there is my voice you have recorded, and due to different noise or different something, it has got degraded. So my objective is that can I reconstruct the original quality? Know? So like you might have noticed whenever you travel in a bike and all this thing, when you speak to your friend or speak to your friend over phone, the other side, so many noise it comes, like bike, the sound of the bike and motor and all those things. Is it possible for me to get back that original signal? Okay, as a human being, we are very, very good enough to do it, and this is where this all approaches of artificial intelligence that comes in picture that play a very, very important role. Because why do you call artificial intelligence? Because you have a natural intelligence with you, which with you are solving the problem. Can I use invite those? Can I motivate my algorithm from that perspective to basically develop this thing that's called artificial intelligence? Okay. So this image restoration problem, if you look at it, I want to first talk about it, simply explain what is a super resolution problem, what are the general aspect has been used, and how it can be used when we're looking for the context of MR images. Okay, so that is where we'll be looking at. So first I want to talk about it. What is super resolution problem? Okay, so the super resolution problem, as I mentioned, resolution, we talk about the spatial and temporal resolution. Spatial means the images which you are acquiring it has a less number of pixels in the rows and less number of pixels in the column. And this is a particular example I'm showing. It's called low resolution images. And this I'm showing is the high resolution images. Okay, so this you might have noticed that when you taken a camera which of not so high cost, and if you work on this, the acquired images of this code. Nowadays, everybody has a smart mode, you are able to get it, but simply you can make with a feature phone like a Nokia earlier days. And if you take another like in a Google, what is that, iPhone 16 or iPhone 12 or 13, that is already there, the quality of image is going to be very, very good. So with this, you can say that resolution. No? So the goal is that this is the LR image grade. We have it, and from there, I want to generate in a high resolution image grade like this. So this is like an image of a simple 9 cross 9, and you have a 3 cross 3. From this 3 cross 3, I want to generate 9 cross 9. So you can think about it that let me put a 9 cross 9 grade something, and then let me put this one image observe here, and the remaining value I need to fill up. Is that making sense? The super resolution problem. So basically, this value I don't have it, and my objective is to fill this value from this only, and this is called super resolution. Okay, so this super resolution problem, when we want to work, this has not only benefit in the medical domain, but it also has advantages in the surveillance camera. So this typical example I'm showing all of you might go to any shopping mall or any place where you know there is a surveillance camera is there, and when you acquire image, if you zoom it, it looks like this. You can see the number of pixels that is there is a very, very small, and the quality of image is like this, and you are not able to make out. So if you develop an ND algorithm which will improve the resolution, it is going to be much better, a good, important thing for you. So this basically I want to show that this improving the resolution has not only like importance in medical domain, but it is very much important in the other domain also. However, I would like to add that all the approaches which has been there, mostly initially it was developed for the natural images, and now people are exploring in the healthcare domain also, especially this context was called medical resonance images. Okay, so what is the intuition behind this thing? Okay, so this is an image, and we know when we take an image from the camera, so basically we put a different uh, sample. This is what the digital image. If you go for very, very fundamental of sampling, so you basically take a sample, and you can see at this each point you are acquiring that amount of light reflected from that object. Can you see here? This is your sample 1, 2, 3, 4. Different samples. You have it. Okay. And the distance between these two samples is your call resolution. If this distance is very, very small, you are able to capture the minute differences. If the distance is very, very large, you are not able to capture it. Okay. So basically, low resolution images, distance between this is going to be high, and high resolution distance is going to be small. Okay. So when we work, how does it work? Let's see. Suppose due to limitation, you have acquired a low resolution images, the distance is 2D instead of small d. Okay. Now what we are doing is, instead of acquiring only one images from this 2D sample grid, you acquired more than one images. So slightly you take an image and slightly shift it. So you can see here, the difference between these two is that initially I took a sample 1, 2, 3, 4, and now I'm taking a slightly shifted and I'm taking it 1, 2, 3, 4 sample. Okay, so 1, 2, 3, if you look at it, now I can have one more, I can have one more. So this nobody can stop me, correct? Because notice thing, I have only the camera which has a poor resolution. So instead of taking one image, I take several images. In this case, I am taking 4 images. So you see 1, 2, 3, 4. Now, since I have this one, and this, please note that one of the thing I want to say, if the shifting of this camera satisfies property, there is something called subpixel camera. If it satisfies some specific properties, then I can try reconstruct the high resolution image by simple interlacing it. And this I can look at it here. Can you see here? I plug in all the black dot which I have got it. I plug in this all blue, this thing, And if I interlace all these four images, I can generate high resolution images. Is it making some sense to all of you? Okay. So when I do this, then this is the idea of generating a high resolution images from several low resolution images. And this is the idea. And this is precisely what's right. And you can think about it. Now here, the displacement of the camera it can be arbitrary also. That is what the scenario is doing. Okay, how do you camera? There has to be a constraint. Okay, what happened? There is no this weekend. So I just thought of this playing this animation, but it is not working it here. I have this low resolution image, this
लिंक दे देना मुझे
several low resolution images.
दूसरे
In this
वाले
low resolution, I'm combining it and I'm
और कल
generating
का
this
दीपक
two
रंजन
images.
नायक का इसका निकाल के
Simply
रखना पड़ेगा ना
interlacing
कुछ
it, and
बोलने
you
के
can
लिए
see
इसका
here
लिंक्डइन से
it
इसका
read the
प्रोफाइल
text called
इसका
can
लिंक्डइन
you
है
read this? On the other hand, it's very
हाँ
difficult to
एक
read
पेज
this, what is
ब्रीफ
the content of these images.
दीपक
and
रंजन
you read
नायक
this.
और महेश को लेकर
Okay, I hope. Okay, so now when we do it, it looks very simple, correct? But what are the challenges? One is complicated motion because this images which you are moving from one position to another position, it's not that you are going to acquire like a perfect this thing because this example you look at it, I'm just interlacing this very well, correct? But this movement of this camera is not going to be so simple. It's going to be very, very complex. Sample, when you take a sample, it is not going to be pinned on, it is going to be some kind of blur. So that is what the sampling is not a point operation. It is going to introduce some kind of blurring. It's like how if you take a for sample from a one small hairpin and as you take a sample from a small nail, other one is going to be like a bigger thing, others other will be smaller thing. So that's
बात
what
में
it is
आती
going
है
to bring. That is not point operation. It will bring some kind of blur in this thing. Okay, so this blur is going to be there. Then there's going to be some noise. There's going to be changes in the scene. Okay, so if you address it, so let's see how do we get it. And basically, this idea is going to help you to understand to like the situation. Okay, so first we are trying to understand this. Okay, so let us first take it this image formation. You have a high resolution scene and you think about it, it has gone through some geometric transformation and then it has gone through a optic blur and it has gone through downsample and the low resolution image is coming. Okay, so just when we look at it, this low resolution images, basically we are writing it that if you want to get from here to here, you can go through this kind of operation. Either you want to get from here to here, you can get this operation. You know? So this high resolution images, you slightly shift it, blur it, and then take it every alternate sample. You will get a noise, low resolution images. Okay. So this is what is going to be this linear operator. You have a low resolution images that is acquired when you apply different kind of this operation on this high resolution images. I hope it's clear. Okay, I'm just repeating it. You have this low resolution images which is acquired when your high resolution images has gone through this operation. So basically, you are taking it that writing that the problem in the mathematical formulation, you have high resolution images, it caused gone through a degradation, and you are acquiring a low resolution images, and you can write it. And decay is basically an operator that is responsible for the sampling. HK is the operator for the blur, which is movement, and FK is the geometric transformation, which you have worked on slightly shifting it here and there. Okay, so now the goal is how do we mathematically write each of these operation, and once we write this operation, you need to solve this inverse problem. Okay, so I'm saying that some kind of transformation number was there, I'm dividing by 2 and I'm telling you 10 by 2 5. So basically you need to know that what kind of degradation has happened, like 5 into 2 multiply, so that basically that when you have degraded it, the division has happened, and when I want to get back, you need to apply that inverse operator, and that is where This problem is also known as the inverse problem in the field of image processing and self-referential. Okay, so when you want to write it, so first thing is to write this in a geometric transformation. Okay, the geometric transformation, basically this is an image, and can I do it will look like this. So for this you can think about it. Basically this pixel is moving from here to here. Okay, so this I can write it in the matrix form. I have a vector, I'm transforming the image. This is the matrix I'm multiplying it. So basically the earlier location was this, the new location has become like this. Okay? That makes sense, or geometric transformation. This I'm sure all of you might have done in a linear algebra and the course where you do study on the geometric transformation. Okay. The geometric transformation which you are looking, basically you are trying to represent in a mathematical formulation in this form. Okay. Similarly, okay, one more thing like this, when we're writing it nowadays, there are some applications which are available which can learn from the design side. And to the optical blur. So, what kind of optical just like in a, due to the lenses that is I mentioned, that you cannot do a pinpoint, so you have a different choice. So this will include blur, and I'm writing it typically the blur operation we say is a Gaussian function. Okay, and this is what I'm showing it here. I'm sorry, it is. Are you not able to see this image? Can you see this image? This pixel? Are you able to see this image? Pixel one?
Sir,
Okay. Okay. So you can see that basically this is the pixel, and you are multiplying with the point spread function. It is going to look like this. So the point I want to emphasize it here: whenever you do a sampling, it is coming with some kind of blur. Okay. So now we are going to write mathematically how this superposition problem is looked at. So we assume that you have the YK images. Anna? You have images YK means Y1, Y2, Y3, Y4, Y. You have several images of the same shape. And each image you are looking at that you have operator HK, that is your like DK is downsampling, FK is a translation, and HK is your blur. Okay, and WK is a noise. Okay, so all these things are with you. Okay, look at like we are just trying to make a case to understand where we are interested in finding out the high resolution images. So we just now will look at an example of an internet situation, and this internet situation when you take it, you need to put it in appropriate. So that's where the mathematical formulation you need it HK, DK, FK, and WK. Okay, and YK is basically the noisy blur downside images. HK is this, DK is this, FK is this, and WK is going to be this. Okay, so basically this is what we are writing it. Okay, you have Y1, Y2, Y3, Yn. You have some kind of n images of the same scene. Please note that the scene is not changing. Okay, so first I'm trying to explain you. First I'm trying to explain you the like superposition problem in the natural images. Then we will like, go to the MR images cases. Okay, so you have a Y1, Y2, Yn images, and then you have a D1, H1, F1, D2, H2, F2. This kind of operation has gone to the actual images, and there is a noise. So you are getting it Y, D, H, F, V. So this entire thing I have written Gx plus V, and this if you it is going to be a resolution factor, and you can work out what is going to be dimensionality of this equation. Okay, the dimensionality of this equation, and now what is your goal? You look at it, you have to find out x from all this solving this equation. So basically, you understand you have a k different observation, and you have only one original image. This one original image has gone through this kind of degradation, and you have resulted to an image, and you are trying to get x such that if you perform this operation, error between these two is going to be minimum across n observation. I hope it makes sense. is going to be the same. Yeah. Yeah. Excuse me. Any question? Yes, you are right, Supriyo. You have mentioned the affine transformation. I'm sorry, I saw the question just now. Your response. Okay, you're right. Okay, so we want to solve this problem. Now, often this problem is Hilbert's problem. Can somebody say what is the Hilbert's problem? Anybody is aware of? Yes, I'm talking with respect to. What is Hilbert's problem? Supriyo? So basically, ill-posed problem is basically it says that let's say there's no unique solution. Like if you slightly change the solution, slightly change the condition, you will get a different outcome. That's the meaning. So this is like if suppose if you solve the problem and instead of choosing this y1, y2, yn came, if you change one of the example images, the solution may change. That's why it's called ill-posed problem. Okay, so what happened in order to solve this problem, we typically add a constraint, and this add a constraint, I'm writing it here, that some kind of constraint, and one of the popular constraint is the smoothness constraint. The idea of the smoothness constraint is that the idea of the smoothness constraint is that typically the images are smooth in nature. Okay, so with this, basically, if you solve this problem, we are going to get this result. Okay, so this is what I want to show, that this is a classical method to get high resolution images from the given scene. So you have a several low resolution images. From there, you are doing it and you are generating a high resolution image. It will look like this. Okay, I hope it makes sense to all of you. Okay. Several you have a low resolution images. From there, I'm trying to generate a high resolution images. Now, what happened? As we notice, the situation is like this. You cannot demand to acquire so many images of the same scene. Sometimes your environment or situation or application allow you, but there will be a situation where this condition cannot be met. It is too demanding that you are asking the person to provide the images of the same scene, several images, and you are looking at that. So this solution was there initial days, but however, it didn't go further. Okay, it was highly impractical to demand, and on top of that, as we'll see, now you think about in MR images. So, do you think that you want to ask a person to be there for longer duration? That is also not desirable, correct? So, this condition of asking first to acquire several images of the same scene, as well as then it has to be the specific condition, that it has to be properly shifted so that you can really, there is no overlap, and there is some condition has to be met. So it's a very, very difficult situation. That is where the other scenario came, is called example-based superposition. So what it says that typically it has been observed that if you take it all the natural images fundamentally at the micro level, when at the 3 cross 3 or 5 cross 5 pixel XL, there are a lot of similarities there. And this arises because you can't ask to have a several images of the same scene, correct? So that is where the idea of example-based super resolution has come. So basically here, the way it has been done is for employing a cross-scale patch redundancy. है ना? So it says that build a cascade of decreasing resolution images from the low images. And for each patch in the low images, search for nearest neighborhood with the even low resolution images and look at it. So I want to show this by this case. Can you see here? Okay. So this is a very, very fundamental view. You will get an idea when you work on the super resolution problem. Okay. So you have these low resolution images, And from this low resolution images, you want to get back the high resolution images. So what we do, you have some high resolution HR images are there. From this high resolution images, you will take a patch and you will generate a high resolution patch and the respective resolution patch. Okay, and this association you have it. Now this association you have it, so what we do, we typically get this LR images. From there we simply interpolate it and we generate like a very blurred thing. And this blurred thing we look at in this data set. If it is match is there, then we find out the respective high resolution patch and keep it there. So this is the way we are going to generate a high resolution patch for each and every high resolution patch for each and every high resolution patch for each low resolution patch. And if you keep doing it, you are going to get it the high resolution camera. So basically, the problem has been decomposed. That instead of looking for the high resolution images for the entire this thing, why don't you work on the patch wise? And each patch you take it, and this patch you develop an association function. And this associative function, if you have it, simply you look at the respective low patch and it can work. Okay, so this is where we can basically generate a high resolution images. Okay, fine. I hope it makes sense to everyone. Just now what I look at it. The earlier case, we were trying to borrow the information from the same scene, but in this approach, the condition has been relaxed. Here, just we are buying it from the example images, and it is in hope that these HR images are considering the broader, what is all kind of example which you can have it. And you can definitely put this question here, is it possible for me to extend this scope for medical cases? So if you have your example images from the natural thing and if you want to organize it, it won't work. Okay, it won't work. That is what I want to say it here, that it won't work. Okay, so what we do, we basically try to anticipate this is going to be my domain. In that domain, we are going to acquire the basically patching level, and this patches basically you are going to generate a high patch. Okay, so here the important thing to notice is that whenever you look at it, that the patch is similar. So unfortunately, we don't get a single matching. Okay, we don't get a single matching. You know, we don't get a single matching. So what happened? Basically, if we relax this condition by writing it, okay, x equal to AC, where A is a dictionary and C is a coefficient matrix. So basically, the patch we are writing it is a linear combination of patch instead of saying only one patch. That's very logical, correct? And that is chances is going to be very much realistic in this scenario, because now you are not putting a constraint that it is similar to this patch, but it is coming to a similar when I take a linear combination of some patch and then I can get it, and that is precisely has been done here. You see x equal to AC. Okay, now when we say A, we call it the dictionary because the dictionary have several patches, and I want to solve it. This equation x minus this y minus AXC, it has been defined by solving that y minus DHAC plus lambda C. You can see this is y is the low resolution images, and AC is your high resolution images, and it has gone through a kind of degradation D and H because you know already what kind of degradation has happened. You know that there's going to be blurring operator. So once you do this, so you are putting a constraint that your coefficient C is sparse. Okay. So basically, once you solve this optimization problem, you are going to get a coefficient, and then you can do a resolution batch. Okay. So when we do this high resolution patch, when we solve it, this problem, the L0 norm, which has to be solved. So as you know that this is an NP hard problem, and this NP hard problem, there some solutions are there. You can prefer it, and it has really led to this one. Okay, so this is the second approach, which has been very popular when we want to do work it in this side. It's like you are taking example images. Now there is a third scenario, which says that I don't have that example images also. Okay, I don't have that example is also. So that third category is called super resolution from a single image. Means neither you have been given multiple images of the same scene, neither you have been given external images, because the external images, the drawback is that if it helps you to get the solution, but it may misguide you. For example, you may do some one of the example you have got it from, which is not at all there in database. What could you do? Nothing. So that is where people wanted to realize this condition, and they say, how can we improve the resolution if you have only single images of the same scene and there is no single external images? This is called self-similarity based methods. Okay, so in self-similarity based method, what happens? We take an image and we do a downsampling at several scales, and then you generate from this other several patches basically. So basically, what has been said that in a given images, there are so at patch level, it's a very high resolution. Even it's a low resolution, but this patch level, the information is very, very rich. So instead of borrowing this patch level information from external images, why can't we borrow the information from the same image? And that is what is called self-similarity. And this approach has been very, very popular in this field, and you can see is going to be a lot benefit in the real world application. You know, you don't have to go for asking for this thing. Okay, so once I give this overview, then we will go for the practical cases. So here, just I want to show one result which we have received and which we have got it when we were working. That when we want to solve this problem on PHSC, there is a constraint. So we also put a constraint that edge preservation. So basically, you can see in this case, I have original images, and this I am showing inter-report images. When you take this gradient at this particular location, you can see that original and images, the gradient is almost aligned, and you can almost argue that this part is not that visible because these edges are not so strong. So there is something called weak edge and strong edge. So almost strong edges are very much aligning here. So this is what the constraint has been exploited when we want to work it out. And this has really helped to basically improve the result which we want to look at it. And you can see that this particular images were resolved, and the box region, if you look at it, you are able to see the edges has been preserved. Okay, fine. So can we take some question and then I will go further before going? I'll just take a 1 minute break. Okay. Uh, am I fine? Is it? I'll just take a 2 minutes break and we can continue on this. Hello. Hello. Can you hear me?
Yes, sir.
Yeah. Well, like if you have any question, I just want to take a small break, and if you have any question, I can address it on this break. Yeah. Then I'll start it. I'm just giving a 5 minute break to everyone so that because it's almost more than 1 hour that all of you have listened me, then I will cover it any point which you want me to clarify.
हेलो हाँ ये मैं डॉली बोल रही हूँ मेरे को डायरेक्टर सर ये अभी रिसेप्शन से फोन आया था कि राकेश जौरिया
So since I'm here itself, do you have any questions or something you can put it? Any
प्रोग्राम तो 10 से 5 है ना पूरा मतलब नहीं कोऑर्डिनेटर को तो मैं बैठी हूँ 5 दिन का ही कुछ एमटेक से रिलेटेड डेटा चाहिए क्या हमको और किसको किसको बुलाया अच्छा
Yeah. Hello.
हाँ जी
I will start at 4:20. You can take a small break and we'll
ओके
go. Okay.
ओके
Just
जी
small
जी
break because it should not look in a continuous video from here. Okay.
ओके ओके
We'll begin. And that is 2 minutes. I'm
ओके
fine.
सो
Yeah. We'll just 2 minutes. We'll start. It's a 4:17. We'll start at 4:20.
okay so all the participants are requested to be connected with this link. We'll start soon. After 2 minutes, there is 2 minutes break.
हेलो। हाँ मैम बोलिए।
हाँ और किसी को भी बोले हैं क्या मिलने के लिए?
हाँ बोले हैं ना मैम, और भी 2-3 लोग को बोले हैं।
किनको?
हाँ
और किनको किनको बुलाएं?
और किसको बुलाए हैं मैम, मुझे लेकिन बताना नहीं है वो।
अच्छा नहीं मतलब मैं कह रही थी कुछ डेटा मांगने के लिए बुलाए हैं क्या क्या है फिर भी मेरे को बता
हाँ
सकती
हाँ,
हैं?
डेटा वेटा की नहीं, जैसे अकाउंट से बोले हैं, ये यहाँ से सुनीता मैडम को बोले हैं, HR ऑफिस से बोले हैं, ऐसा है मैम। ऐसे ही। हाँ मैम, जय मैम का कॉल है ना, मैं रख रही हूँ।
हाँ
हाँ
हाँ वो रिसेप्शन से फ़ोन आया था कि वो राकेश रजौरिया जी, वो डायरेक्टर सर का कहना है कि राकेश रजौरिया जी बुला रहे तो वहाँ जाके मिल लें 10 मिनट। तो मैं पूछी क्यों बुला रहे हैं? तो फिर मैं पूछी और किसको बुलाया है क्या है? तो वो बोल रहे हैं कि 2-3 लोग को, मुझे लग रहा है कुछ डेटा चाहिए क्या, या तो एमटेक से रिलेटेड कोई डेटा चाहिए, पता नहीं क्या है भाई। तो मैं
तो आपको बुलाया है तो?
अब पता नहीं मालूम मुझे कि क्या है वो
नहीं, तो फोन आपको जाने के लिए बोल रही है।
हाँ मेरे को जाने के लिए तो बोली है कि वो बुला रहे हैं वहाँ पर। मतलब देशमुख सर ने बोला और तो मैं बोली और किसको बोली, तो वो फिर रिसेप्शन से पूछी तो बोली कि और भी जैसे सुनीता को बुलाए थे थोड़ी देर पहले, और किसी किसी को बुलाए थे। तो अब क्या पता क्या है, बोली भी हमारा प्रोग्राम चल रहा है, तो बोल रही कि वो अब 10 मिनट जाके आ जाओ मिल के। किस बारे में हो सकता है?
खत्म हो गया क्या सेशन?
नहीं, अपना सेशन ख़त्म नहीं हुआ है। हाँ यहाँ बात नहीं करो क्या, ये सेशन खत्म नहीं हुआ, वो बोला कि 5 मिनट के ब्रेक देते हैं। इसका तो 5 बजे तक है, तो ये हाँ। अरे माधुरी है कहाँ यहाँ पे नहीं है ये तो है। कहाँ गई थी, क्लास में नहीं गई थी क्या? मेरे तो क्लास में नहीं है। मुझे अभी ये टेंशन हो रही है कि ये क्यों बुला रहे हैं? नहीं कुछ नहीं बुलाने वाले ना, कुछ और तो नहीं है ना, क्या पता। अब बुला रहे तो जाने तो पड़ेगा, मैं बोली भी चलो तो क्लास में मेडिकल। क्या पता है, ऐसे ही है।
Hello. Can you hear me? Hello, ma'am. Can we start?
Yes, sir.
Yeah. I just use a small break. So I think one of the questions which has come, can we improve the resolution image by zero padding? Yes, it's a very simplest and one of the oldest approach. Now people are very much keen on doing, what do you say, doing this. This will give you a very fast result, but people want much better improvement on all these things. So you will not get a kind of improvement what the different design machine learning algorithms are giving. You can do it, but the quality may not be as good what today
माधुरी
trade or
मुझे ना
state of the art approach
कहाँ
is
से
giving.
बुला रहे हैं अभी, तो
Is it
दो
fine,
मिनट
Supriyo?
तब तक देख ले, मेरे आते
My,
तक 10 मिनट में
did I answer your query?
Yes, sir.
अच्छा लैब, हाँ ठीक है। वो ना लिंक भी शेयर
So,
करनी पड़ेगी
so
कि जब जहाँ
now, Mama, like, if you recall
तो
how we
अभी
have gone
देखते
through it,
हैं।
I try to give you that reconstructing high field images or improving the resolution of MRI images or improving the contrast. And before going thing, I gave a brief background of what are the different approaches that are available for the natural images. So one of the approaches was using several images of the same scene, then using external images and third single images. And if you look at it, you will say that definitely I will be very happy if I can take in images a self similarity, like that single image correlation. Why? Because it's very difficult to get the MR images for the several people. It's not easy. Second, the brain size and all alignment and everything is very, very challenging. Third, the solution is ruled out where you're asking uh, multiple images of the same scene. So basically here, the solution which is very, very apt for this application is single image resolution, where you are trying to generate high resolution images from the same scene. Now, when we want to do it, you look at it, one of the beauty of this thing MR is that you have entire volume. Okay, so when you acquire the images, you have several cross section. So this cross section can be used very well, and that has been looked at it,
हेलो,
and it is very important that
हाँ
we
हाँ
should work on the single image approaches. Okay, so with this, this is the work of the PhD student when she was working. So what I want to say that existing approaches basically they demand several example of it. There are some approaches available, and the difficulty is that you don't have enough amount of data. Second thing is whenever you are improving the resolution, it is bringing some kind of artifacts. It is bringing some kind of blurring between the tissues. So the goal is that our tissue boundary should be very clear. That is, otherwise the doctors and all these things, the clinician which we look at, they may not be very happy. One thing I want to say that these solutions are still not in the state-of-the-art scanner. It is coming out if you look at it. So whenever we discuss with the doctors, they say, no, the tissue quality has to be really, really good. Okay. And third is that reliable application of process image is also not known because sometimes you are interested in identifying a tumor, sometimes some other kind of thing. So it's very, very difficult. So that is why we want to get it. So in that direction, the initial approach which we, one of the things this was published in one of the conference called Medical Imaging Computing Conference. And there, what we did that, okay, this is the constraint, if you recall, of super resolution is sparse resolution, y minus b h e alpha plus alpha 1. So basically here, this, when you are looking at this, A is a dictionary which you are forming from the already several patches available of the same human brain image scanner. Okay, and this B and H is basically the blurring and downsampling operation, and this alpha is a coefficient which earlier I was using a Z, so I just changing the notation that has become. So you are trying to minimize the L1 norm of this function, you can get a solution. Now the thing which we did it that we added a constraint. What we added a constraint that gradient profile sharpness. So basically, if you look at the edge, like a preserving constraint, which we talk about in natural images, similarly, we look at it here that what is the gradient profile, okay? And we want to ensure that this gradient profile in the same scene when we are looking at it, we want to make it as small as possible. Please note that these two are because here we don't have you don't have the real images. So for that, what we tried it, we went with the like some kind of database. We look at it. Already we compute the histogram for high resolution images, and as well as we try to look at the relation between these things. And what we observe, it is following a linear relationship from this vector. So this linear relationship we approximated, and then we have shown the result. So this is what we tried it, that whenever we want to improve the resolution of the MR images, we are using the simple image concept, and we have solved this problem of this by basically using this edge profile, and basically using this constraint which try to minimize the GPS, gradient profile sharpness. Okay, so basically it's an unsupervised approach. It is comparable performance to the existing unsupervised. So why it's an unsupervised approach? Because you are not asking the already paired images. Okay, and this we have evaluated it, and you can see the quality evaluation basically when we observe, it is really giving a pretty good result. The second problem which I was talking about is improving the resolution, which is noisy. So it's very much, what do you say, very much natural that whenever we work, the acquired image is going to be noisy. Okay, when acquired image is going to be noisy, so the problem we pose is, okay, can we improve the resolution of the images when there is a noise? Okay, when there is a noise. So here, when we look at it, the approaches which they look at it, again, they have tried to extend the same method which were already available in this improving the resolution case. So now all of you can say that, okay, let us try to solve this problem first, denoise it and then improve the resolution. Okay, nothing wrong. Either improve the resolution, then do the denoising, that is also fine. But what I want to emphasize on this aspect, the moment you do this operation, in isolated manner, so any of the error which has come in a step one, it will propagate to the step two also. Okay. So the point I am emphasizing is that because you have a step one of denoising and step two of super resolution. Now suppose there is an artifact has come, it is definitely going to be enhanced. So the idea came, can we do in an interlaced manner so that, can we do in an interlaced manner so that this can go in an iterative way, okay? Do a denoising, then resolution. Then go to another step. So this is what we have tried to look at the interlaced. And when we are working on this, what one other thing it came, we took a very simple approach that is called principal approach. So here, if you go to the basic concept of this, that component patch, we write a linear combination of eigenvectors, and if you eliminate the eigenvector which is responsible for the low eigenvalue and basically suppress the noise. But when you want to do it, what we observe that you need to choose that what is the optimal number of eigenvector which you want to use it. So if you have images with a high SNR, which is very good, you can work out with a very low value of vectors. But if your image is not having a good high SNR, like you may have so much of diversity in images, so you will have the image patches where SNR is not going to be so great. So there what we can use that you dynamically change this lambda. Okay, so this is what we have tried on this thing, and we were able to get a pretty good result on this. And this we have observed for several cases, and you can notice that this is the noisy images, and these noisy images, this is what we are talking about already existing approaches, which is trying to improve the resolution, and this is a proposed approach which we have talked about it. Another thing, whenever we work on the denoising, what happened? We assume that what kind of noise it has been affected. Okay. Um, hmm. So, what kind of noise it has been affected? So, typically, we take a prior assumption the noise is Gaussian, or might be some kind of gamma distribution or different type of distribution. So, the point is, the moment you take some kind of assumption, that depends on whether your noise is having that assumption or not. So, this approach has not taken any assumption. Okay. The third problem, which I did talk about it, reconstructing a 70 like MR images from the 3D MR images. So here you can think about it that the goal is to learn the mapping between 3 Tesla and 7 Tesla. So you know you have a left hand side 3 Tesla images, right hand side 3 Tesla images, and learn the mapping. Down the line, you get a 3 Tesla images, simply you apply the mapping, you get it. But what is the challenge here? You need to have a sufficient example of, to learn this mapping. So in order to explain in a very simple term, you are asking the same person to go through a 3 Tesla snap as well as 7 Tesla snap. Okay. Now look at the difficulty or the complexity. First, we are struggling that we don't have enough scanner. In that, you are asking the person to go through the scanner twice, which is not so easy. And as well as the moment we take a training example, there is going to be some kind of bias also. Okay, so that is where the solution, its practicality is going to be very less. Yes, it works very well, no question of that, and there is a very well-known paper has also come in this field, but there we can't extend this one. Okay, so for that, what we have looked at is that an approach where it doesn't require external images. So for that, we have worked out a solution which I wanted to just skip this result and show this result that here, this when we are doing this mapping and this one, so it's basically y equal to dhx, so you don't have any identification. Simply, both the unknowns are there. So this the unknown which we are looking at, we are trying to solve in a iterative framework. So first, you fix this thing a, then solve for x, then fix the x, solve for a. So when we are solving it, there is a constraint that we have talked about it that let us deal this white matter and gray matter separately, which I did mention, because gray matter is responsible for your like a neural thing, and white matter is responsible for connectivity. With this characteristic, when you observe the intensity values, they were very different, and this constraint was kept to produce the result. Another very interesting observation which we have got it on this side is this is what we look at it. Let us try to reconstruct a 3D like MRI from the one point. And we are again we are focusing on that there is no capabilities available, and we are using the physics-based constraint that we know that how the tissue is going to behave, and I know the physics of that, and that tissue I'm saying that how this tissue is going to behave at the low magnifical strength as well as the high magnifical strength, and these relations I'm trying to incorporate in this particular example so that I can improve the result. And this we got a very really encouraging result, and I want to say that this results like no one has before done this literature, and we could do it. And the result which I want to demonstrate it here, that it is coming, that we also extended this concept. If you want to reconstruct 1.5 Tesla from the zero point 0.2 Tesla images, and this is what is coming. And then also you do from 1.5 Tesla to 3 Tesla images, and how it is going to come out. Okay, so this 0.2 Tesla images, you can see definitely you want to go step by step, or you want to go directly from to here. The result is not going to be good here, and it's a really, really interesting result. So basically, I want to summarize it this first, that when we are doing it, this is for the structural MRI. Okay, structural MRI means you have the images which you are doing it, and due to hardware constraint, you need to compromise on the temporal as well as spatial resolution. And due to hardware also, there is going to be a struggle on the signal to noise ratio also. Then there is also going to be challenge on improving the contrast. Okay, and whenever we want to optimize this parameter, then whenever we are going to optimize this parameter, we need to always balance a trade-off. Okay, and this trade-off basically is going to be not going to give you complete good result, and we need to come up with approaches which is going to really give a cushion to your hardware. And for that, whenever approach is going to be, we should be looking for approaches which doesn't require some images, it doesn't require your taking several images of the same scene and trying to reconstruct. Right. So with this, I just want to summarize it. That first part of this is like a structural. I hope you have any question, and I can take it, and I will spend around 20 to 25 minutes on the functional aspect of it. Yeah, any questions on this? So far what I have explained, it is a structural MRI. Okay, fine. So now I wanted to cover the second part of this thing, is looking at the functional aspect of the MRI. So this work again, I want to say that my collaborator, one is of course Bharat Biswal from the NJIT, and I have a MS student who works on IT Mandi, and myself is there. So I want to talk about it. Okay. So what is this? So far, what we have looked at it, you are asking a person to go through the scanner, and you are trying to understand the structural aspect. Now, there is another another study that is required to understand the functional aspect. For example, as all of us know, that brain has a different part, and we know that some part is responsible for the visual cortex region, some part is responsible for you to language aspect to understand. So this kind of concept has been developed. Now, there are some people, those who are going to like a neurological disorder. For example, somebody is having a dementia, or somebody has Alzheimer. So this functional aspect has been somehow doesn't work the way it has to work for the healthy person. So there is a huge demand for us to. Yes, someone is having any questions on this? Yeah, any question on this? So, okay. So there is a huge demand to understand. So when we wanted to ask what happened, there are two modalities that has been explored. One is called EEG and it's called fMRI. So in EEG, you might have seen some people do research. They have a cap and they measure the observed signal from this. Okay, so basically this signature is going to look at that what kind of function is happening here. The other modality is fMRI, where what has been noted that whenever there is some activity in that particular part of the brain, then basically there is going to be a huge amount of oxygen. And the huge amount of oxygen basically is going to look at it as some kind of signature that is called bold signal. blood deoxygenated level dependent signal. So basically, this bold signal has been acquired to look at it, and it has been observed that that bold signal basically it does give the information of your uh, activity on this region. Okay, so this two, I mean, there are other than this tumor, there are other modality also exists in this area, and I just want to say that fMRI is a good choice. It's not that EEG is bad, but there are some comparison. fMRI give a very good spatial resolution, but it is relatively poor temporal resolution compared to the EEG. Okay, and second, the electrode plays on the scalp, hence only cortical brain signals can be measured. But here, since we are measuring by RF pulse in MRI, hence cortical as well as cortical region can also be measured. But only thing is it is an expensive as compared to this thing, because your MRI scanner everything is going to be in order of crore. This EEG is going to be much cheaper than this solution. So what happened? This is what people are trying to get it. So this paradigms has already studied in last 20, 25, 30 years. And here what happened, a person had been asked to go through the scanner, and the scanner, when they go through it, there are two scenarios they measure the signal. One is called task, another is called rest. Task means they will be given a some small task, maybe when you look at some object, so put your finger or move your toes, or different type of tasks are there. So what will happen when you do this task? It is going to be some kind of activity will happen, and this activity is going to trigger some kind of activation, and we will have a signal. And basically, the goal will be that we will observe that signal so that it can be used for any analysis purpose. In a resting state scenario, they don't give any kind of task. They simply ask that person to either open the eyes or close the eyes. So in both the scenario, they look at it. And when they look, observe, so they try to match it that the signal which you are observing from the two different locations, how correlated are there? And that is called functional connectivity. Okay, so this functional connectivity is of great interest that comes, and how do we measure it? I just want to demonstrate it here. Okay, so you have some kind of time series that you are observing from different location, and I'm showing, suppose there are n different region, you can see there are different n different region. So you have an n time series, and this n time series, I'm saying it is your bold signal. So this time series, basically you are trying to compare the correlation between this thing, and you are matching it. So I'm keeping a matrix is n cross n, where n is the number of region, and 1 versus 1, if you look at it, it's going to be highly correlated. That's why it is I'm marking the 1. And if you take it this particular with respect to 2, I'm going to get correlation value here, then 1 respect to 3, 1 to 4, 1 to 5. So this basically is going to give that how two regions are connected for a specific task or rest condition. Okay, does it make sense? That how these two different regions of the brain are present, and this is going to be a characteristic of the human brain. Okay, and this particular is going to be a symmetric matrix. Upper half diagonal is going to be same as this because the same region is going to be covered. This is called functional connectivity. The two thing comes here, okay, when you record a data, the recording can happen for some minutes or 10 minutes. So somebody can say, okay, there is not going to be one connectivity because you are going through a different thought. So that is where they observe the dynamic functional connectivity. So when we are measuring this correlation, we don't measure with the entire length. We take a small window and try to compare here. So this functional connectivity will be changing over a period of time, and that is called as a dynamic functional connectivity. Okay, so that is why the two terms are there: static functional connectivity and dynamic functional connectivity. Okay, it's a great interest. I just also want to emphasize that when we measure this bold signal, is the third category which has come in the which is called movie watching. So what is the idea? Then when you are watching a movie, you are doing some kind of activity. You are not responding, but you are doing that. So this also people are trying to understand. That is helping people to understand different kind of neurological disorder like schizophrenia or Alzheimer or something. Okay, So basically, you will have a digital connectivity of several subjects, and our goal is to apply any machine learning or artificial intelligence approaches to figure out if somebody is very unique or not. Okay, so this is what I just shown it, that we are using the functional connectivity, and when we do a functional connectivity, we have a like a some kind of template signal. Okay, this particular region should behave in this way. On the other hand, for hosting and destination, the same information is not available. Okay, so one of the things which we want to try, that we know that human face image, correct? This is the human face. You can see all of you that it is Barack Obama as a some person. So when you look at it, all of us have some two eyes, one nose, and these things. Still, there is some kind of uniqueness. Okay, and all of us can simply identify that down the line. Some of you met me, and you can say this person is like this. I can see is this. Even this is a caricature of American President Barack Obama, and you can say that there is some kind of unique characteristic. Okay, and this may go to any film actor or actress or anyone. So that's what we want to attempt it, that is it possible to identify some unique aspect of the functional connectivity, and we wanted to look at it here. So basically this is where we have tried out, and what we have tried to look at it, that write a function connectivity which is linear combination of common function connectivity and specific connectivity. That is the idea we have tried out, and it really gives the very good result. And here the only question comes: how do we measure how do we measure that what subject specific connectivity is coming out good or bad? So what has been done here? That okay, let us try to estimate this for the two scenario. Let us take some ask the some subject to go through some 10 or 15 scan and use a 5 or 10 scan to estimate this unique characteristic, and also you estimate this functional unique characteristic for all the session. If it is coming from the same subject, it is going to be highly similar. It is coming from the different subject, it is going to be very, very different. Okay, so with this we want to look at it, but here you may say, okay, the same person may not be here, that kind of variation is going to come, but it has been studied that this situation is more or less saturated. I won't say saturated, it's more like steady, like a state, reach to steady state situation where you can say that what is the unique characteristic. So this is what we are trying to look at it here. Okay, so with this time, then we can compute the connectivity and we can identify. And here also, when we are looking for, can we be a specific to a situation where we are saying that this unique characteristic is emphasized in this region. So there is something called default mode network. The default mode network means a network which is responsible when you have gone through a rest condition. Okay, so is going to help you to bring out the unique characteristic. Okay, different things are there. So with this, I want to just summarize this and close it, that okay, I did mention about this functional connectivity or the dynamic and functional connectivity, and like of the different brain region, and what is the very important thing is what are the different representation of that thing, and we are trying to estimate it, and as well as there are different processing contexts, from phase-based measure and correlation-based measure. Several things comes to picture. So with this, I just want to stop and then take some questions if you have it. Actually, there is one question, that can correlation be used for image and speed features? In yes, very much. You are right. We can use it, and this approach has been there. But now people want much more complex way to represent your signal. There are two aspects. What you are observing it, you need to suppress the signal, and you need to measure in such a way that you are going to correlation between signal very well. Okay. So any questions you want to ask? I can take some questions here.
Thank you so much, sir. On behalf of Department of IT, we are very thankful for your knowledgeable session on various technique in the diagnosis prognosis of diseases. Participants, if you have any doubt, please you can contact you can send your doubt in the chat box, or you can on your
audio, or you can directly interact with sir.
Yeah. I have given my email ID. You can send me email also later. But today, if you have any questions, I'll be happy to address this.
Anyone, if you have any doubt, please you can drop any message, or you can directly on your audio and talk to sir. No query? Okay, thank you so much all the participants for the wonderful session. On behalf of Department of IT, I, Madhuri Gupta, Assistant Professor, very much thankful to all the participants, and sir, we are very grateful to have you. Thank you so much, sir.
Thank you. Thank you very much.
Thank you.
I can log out.
Yeah, yeah, yes, sir. You
Thank
can.
you very much. It's my
Thank you,
pleasure.
sir. Thank you so much. हेलो जी मैम. हाँ 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 हाँ, मैंने कर दिया एंड. हाँ 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 हाँ.